you? Like, so Obiora, how about you? I don't know, your own experience developing products and how this is really great, you know, for you.
Um, yeah, for me, when I found out about this feature last year, and of course, I already saw that this was on the roadmap, and the Fusion 360 roadmap. So, but when it finally came out last year, and I was able to, test it, and as well see the future being used in the Autodesk Academy. I mean, sorry, the Autodesk University, a demo was shown them last year. It was actually very amazing. And like Julian said previously, you probably had to use mode flow, or maybe you even had to send it directly to the manufacturer. And then it takes about 2 weeks. We know the lead time that things like this take. And so manufacturers try to give about a week before they get back to you on what to change. And even then they have to get back to you and you have to make these changes. There's a lot of back and forth that goes on and between you and the manufacturer. And then, but with this particular feature on the Fusion 360, you can very easily take your product and check if it will actually come out nicely. And you can do a lot of the work at a very early stage. So it's actually great, yes.
Yeah, thank you, Obiora. I think I really love that part of collaboration with the manufacturer, because I think over some years past. Oh, I can see people like Latif Balogo on the chat. These are people that have done plastic design, and I'm sure they can attest to how much constraint, how much back and forth you tend to experience when you're doing plastic design and you're working with a manufacturer somewhere out there. So, with these, you have the ability to, on your own, make some basic checks, make checks, check your product and make sure that meets the possible requirements. So, but these are, and these and so many more are what we're going to explore today. And as it's about time, we'll just get started right now. So before we get started, quick one, Felix, permit me to just start up the session.
Go ahead, please.
Yeah. So before we get started, just to engage everyone here today, if you're hearing me, just quickly put on the chat where you are joining us from today. So just briefly give us where you're joining us today. Oh, nice. I can see Caleb is joining us from Ghana. That's nice. Welcome, Caleb. Oh, wonderful. We have someone from Nepal here on the call. So that's nice. Welcome, Danu, if I pronounce that well. Okay, so without much ado, I know a whole lot of people will be joining this session much later, given the number of response we had setting this up. So, but we just have to get started, on the hour, because we have to meet exactly the 1 hour mark for this session. So, good morning, everyone from it's actually still morning in Nigeria right now, 11 o'clock a.m. in the morning, and good afternoon from any other region, or good evening from any other region you're joining us. So welcome to today's session, brought to you courtesy of the channel team at Autodesk, made up of generative CAD services, Worldview technologies, and of course Autodesk. So our objective today is to be able to explore and discuss possibilities with injection molding simulation with Autodesk Fusion 360, which is Autodesk one of the best technologies out there, right? Disrupting the way we design and make things. So without much ado, I'm going to start up the session, the early part of this presentation. So just to take a look at the agenda, what we'll be looking at today. First of all, of course, I am leading the introduction, followed by some discussion on leveraging plastic injection molding, why and when. All right. Then we're also going to explore design rules and consideration. This is always around, or specifically around, around considerations for plastic design. And then we're now going to have a demonstration on this injection molding simulation. So which is all led by a team of 3 of us. Firstly, my name is Julian Mbakwe. I work with Autodesk as a business development manager, looking grossly on the manufacturing space. With me on the call is also Felix Hamefula, who is the team lead at Generative CAD Services. And same on this call, we also have Obiora, who also works with Generative CAD Services as an application engineer. So to get started, first of all, I would like to do the intro on this. What exactly is injection molding? What is it all about? Of course, from what you know, it takes a lion's share of the overall plastic manufacturing processes, in which you see a whole lot of other manufacturing processes, but certain features, certain values make it seem to be the most valuable. And in its process of manufacturing is also made up of basically a mold. A mold comprises of cavity side and the core side. And the material of this mold is often from hardened steel or aluminium, all right? The engineers here also knows that all of these have their pros and cons, all right? And it has to do a lot with heat and pressures and all this stuff. And of course, for the raw material, we often have varieties of plastics, but they come in resin pellets. So aside from that, also, it's also very important to mention that there are other plastic forming processes, right? And these all vary depending on the process, all right? So there are a whole couple of them available out there. But often when you're considering plastic choices or manufacturing process for plastic, certain things come into consideration, all right? The form, the complexities, all right? The intended volume, all right? And associated cost, of course, production lead time and material. So, given all of this combination, all right, it's always very, very desirable to go for the best fit. All right, so it doesn't really mean that injection molding is the perfect outlet, but it tends to have the best combination, the best feature fit that favors manufacturing, especially when you're combining volume against cost. So this is something that makes this most desirable. Of course, I've mentioned about its share in the market, all right, or its share of the manufacturing process tends to be the best or the most widely used in the industry. So, but for me, before we go ahead, people often ask why injection molding. Of course, working at Autodesk, this is partly one of the conversations we often have with people. All right, why not? Some people even get to the extent of asking why not 3D printing. So some of these, depending on the features or the benefits, all right, it's quite important to go for a particular desirable feature. So for injection molding, it's quite favorable. It's better. It makes more financial sense when you're going for high volume, all right? When probably you're mass producing some plastic, all right? It also comes in handy, of course, when you're trying to get the best mix of time, quality, and cost, because for quality, it gives you the best. Also, it accepts a wide range of materials and productivity is high. And importantly, when you talk about repeatability, whether you're doing routine production, this becomes quite desirable. So, but what makes today's session very critical, all right? Why is it critical to think about the objectives of today's session? Just as we discussed just before the session, it's quite important to put in place the complexity, the cost, and the design of molds, all right? Because of how delicate and sensitive this is, all right? It's also very important for you to get this into consideration during the concept development stage, during the design stage. You don't really have to wait until the design gets to the manufacturer, the mold manufacturer, before you start considering making some design changes. Also, partly what Obina will also show us today is, you know, the basics of plastic design. You know, as a designer, as an engineer, there are certain things you need to consider. You need to consider why making your design before you're able to have an efficient mold design. So, but I'm just going to stop my presentation here and allow my team, Obina and Felix, to take up from the next step or the next agenda we have today, which is more like the rules guiding this design process. So please take it up from here, Obina.
Yeah, thank you, Julian. Thank you so much. I'll probably take it off from here. So shortly, we just want to go into, just like Julian talked about, the rules and design for products. So I just wanted to just jump into the design rules for injection molding, because it's something quite important for us to know that while we want to talk about injection molding, we shouldn't just wait for the point when we just send to the manufacturer and then a lot of issues comes in. So there are always rules for all manufacturing process, whether it's a sheet metal like laser cutting or 3D printing and injection molding. So it's also quite important for us to know that these things exist, and for us to start thinking about them right from where we are doing our design, like from the conceptualization and design process, so that we're also going to have this, not really going to have this back and forth thing. So the first rule is always like rule one, we call it, is that's kind of use of constant wall thickness. This is very, very important. That where you're designing for plastics, it's very important that you use a constant wall thickness, and the recommended wall thickness is always between 1 mm to 3 mm, because this is quite critical that you obey this rule. That because always design with smallest possible and constant wall thickness tries to avoid warping and sinking. And if the thicker section are required, probably you might need to use you might need to use hollow and then use ribs to actually join them together. It's that can also keep the stiffness. But because if you don't do that and you just literally increase the thickness, definitely you're probably going to be facing a more issues. The cost will increase because the cost of time of cooling will definitely increase. The cost of time it will help you take to fuel that particular plastics during the injection mode will increase. And then as the time increases, that also reduces the time that probably, if you're probably going to manufacture 1,000, probably going to manufacture 500, and that's kind of a cost on the production. So, and then you probably literally don't have any use for it. So it's something that I really wanted to come here. So the rule one is always to keep the edges round, so add fillets, both internal and external. At the same time, the internal edges should be around 0.5 times wall thickness. So that's kind of the rate internal edges reduce. And then an external edges, you probably want to look at the internal fillets, and then the wall thickness. So it's always important that you always keep the wall thickness constant, just as the edges also constant, like the fillet and all that. So it should also be the same thickness with every other wall part of it. So this is something quite important. It's very, very important to note. And then third rule, if you say, is always remember to add draft angles. It's something quite, and then the minimum draft angle, or recommended minimum draft angle is 2 degrees. So you could add it to 2 degrees or 3 or 4, as the case may be, but don't add the minimum. Always add draft angles and don't add less than 2 degrees. It's something quite important, because for parts you probably want to have issues during the injection when you want to inject the plastics and then refill again. If you don't have draft angles, it's actually kind of a problem, which I have kind of a drags on the mark of the body. So it's always very important to have draft angles, at least minimum 2 degrees. So next one will be undercut. Like this is something, a very, very, very important aspect to consider while designing for parts for injection molding. So and because undercuts, in injection molding are part features that you can actually manufacture. Molds come into 2 different parts. Like the most simple molds come like, okay, kind of 2 parts. But when you have kind of undercut, it kind of becomes more difficult to manufacture with simple 2 mold, pattern. So, and because material is in the way, because of complexity and all that, while the mold opens and doing injection. So it's always kind of an issue. And one of the things that actually can cause undercut is one of the teeth of the thread or maybe on the hook on the snap fit. John, these are like examples of undercut. So you can just take note of that. And then how to deal with undercut. So moving the part line. So you probably want to, one easiest way to probably deal with undercut is if it works for that product is to move the pattern line. So that's one, to move the pattern line to the mold to intersect with it. So we move the pattern line for the mold to intersect with that particular part of the undercut. This solution is suitable for many designs, with undercut on external surface. Remember, you have to adjust the draft angles accordingly as regards to this. So next one you probably want to how to deal with undercut is probably maybe using a Shutoff. And Shutoff is like kind of remove materials from under or cut or above the problematic area. So this way the undercut is eliminated as the whole part can be directly supported by the mold. Shutoffs are useful trick to deal with undercut and on internal regions of the part for snap fits, or on the size of the parts for hose and handles, you can actually consider using kind of undercut, unlike the first one. The second one, the third one, we probably want to deal with undercut is like side action cores. This kind of make it's really kind of more complex, plastic products. So because this, we advise that you use this when they are 2 above solutions are not viable or probably don't give you what you want. So then cores can be used that slide out of the parts from side before it is ejected. So side action cores could be used sparingly as they add complexity and increases the overall cost of the mold. So it can increase overall cost of the mold between 15 to 30%, and it's something you probably want to be mindful so that you don't just use it first. You probably want to explore other options to deal with the undercut before you probably want to use the side action cores. So next, we'll probably want to talk about is designing for injection molding features. So there are always very important features for injection molding that you can actually always leverage. Like when we mentioned about giving a hollow, it is more than 3 mm. It's kind of stuff you instead of doing trying to increase more than 3 mm, you probably want to use a hole and then use ribs and all that to kind of hold it. So when the maximum recommended thickness is not enough to meet the functional requirement of a part, you can now use ribs to improve the stiffness. And when designing for ribs, use a thickness equal of 0.5 times the main wall thickness. So that's kind of the real thickness. So you want to use that, wall thickness for the ribs, and then define a height smaller than 3. Yes, that's 3 times thickness. So you have to kind of design the height so it doesn't really get, quite tricky at that point. And then use rib-based fillet, which radius greater than 1/4 of the rib thickness. So it's something, these are kind of things some observations you want to use, and probably you also want to add, again, draft angles of at least 0.25 to 0.5 degrees. So you really want to add that to those ribs. And so this is also some of the things you probably need to consider. Well, really you need to kind of use ribs, especially when the wall thickness gets more than 3 mm. So the next thing you probably want to features you have injection mold is bosses. The bosses are used as point of attachment or fastening in conjunction with self-tapping screws or threaded inserts. Bosses are like circular holes. You can see that in the picture where you have that at the, kind of most times at the edges, or probably maybe at places where maybe the components need to rest on, you want to use as screws and all that. So yeah, so buses are like circular ribs. So the same general design guideline applies for ribs are also applied for buses. So next, it will snap fits. So snap fits, here snap fits are kind of an economical and rapid way of joining two parts, without fastening and tools, without using screws and fasteners and all that. You probably want to use snap fits to actually use that. So in injection molding, you have to add a draft to the side walls of the snap fit. It's very important, and use a thickness of 0.5 times, the wall thickness is also quite important. So, and adjust the wall, the weight and length to control the deflection and fork. So these are some of the things you also want to put into consideration while you are designing, adding features like snap fit into your plastic products. So next is lecturing and symbol. So you probably want to, most plastics you find there, you probably have a text written on it and all that. So, and it's plastic injection molding is great, unlike 3D printing or handling checks and all that, but it also rules to get the best results. Like text logos and other symbols can be engraved or embossed on the surface of injection molding parts. So, but here are some of the tips, why adding text is, if possible, is recommended that you use embossing instead of engraving. So, and again, is to, you probably want to align the text perpendicular to the pattern line. Make sure that the text, that pattern line, let the text be perpendicular to that. And they use a height or a depth if you're using like embossing, engraving, sorry, height if you're using embossing that is greater than, 0.5 mm for, great results and, coming out for the text to be clear and also not to have issues. So use a font with uniform letter thickness. So try to use font that have uniform letter thickness all around, and then probably use font size that should be at least 20. The font size should be at least 20. So these are things you probably want to take note while you're designing features, when you're adding features to the plastic. So yes, thank you, and probably want to hand over now to Obiora to get to show us some kind of case study of how we could leverage from the side that Julian mentioned. So what I just concluded now to the part of that case study where we can see how some of these tools and some of these things are kind of applied, and how Fusion kind of really helps us to get get this thing done, and then give us kind of further insight and an amazing way workflow to kind of solve some of these issues when they arise before sending to the manufacturer. Okay. So, yeah.
Okay, thank you so much, Felix. That's quite an insight, and just to add to what Felix have said, these features, these considerations are quite important, for the safety, for the quality and cost of your product. So if you're complying with the required thickness, the required and of course, if you're preventing undercuts, right? What people don't often understand is that designing shouldn't be as isolated from manufacturing, because when you keep adding undercuts into your parts, the best solution the manufacturers might be inclined to would be to include much inserts, mold inserts, and of course that is more money. So just to continue, so Obiora will now give us an actual case study, all right, with Fusion 360. He's going to demonstrate how this works, simulating for injection molding. So at the back of our mind, we'll start asking questions like, would the part view, will it have sink marks, or are we going to have weld lines that will be detrimental to the aesthetics of the product? All right, are we going to have problem with excessive wrappage? So all of these things are the questions that these will solve. So please, Obiora, you can share your screen and then take us through this demonstration.
And thank you, Julian. And then also, and thanks to everybody that's presented so far. So I'll just go ahead and share my screen. So can you confirm that you can see my screen right now?
Yes, yes, I can. Yes.
Okay. Yeah. Yeah. So good day everyone, and I hope that we've been enjoying the session so far. So in the next minutes, I'll be demonstrating a case study to all of us of how Fusion 360 can help get ahead of your manufacturing processes very early on in the process, right? And then why you can know all these design rules, right? You can keep to constant wall thickness. You can add ribs. You can do a lot of things to ensure that your part comes out great. It will also be nice for you to see in real time what will happen if you take this product to the manufacturer, right? If you put it in an injection molding machine, right? And this is what we are going to be looking at. And I'm going to be starting from the very first process. And then, as we all know, or if we don't know, when you want to begin a design, you have different people on the team. You have the electrical guys, you have the design engineer. You have those that are very well versed in the plastic injection molding, right? And the first stage is, of course, to come up with a prototype, right? And so the first thing you want to do is probably you want to have one or two samples and you want to design for 3D printing. And what we have here is a PCB with different ports. And we have the first enclosure, just one half. And this was designed for 3D printing, right? And also just to note, you can design your PCBs with Fusion electronics, right? Just in case you don't know about that, right? And you can also do your 3D printing right here inside Fusion 360. So when we printed this part, it came out pretty great. It was nice. It worked actually very well. And just to reiterate, this is an enclosure for this particular PCB, right? But after designing this for 3D printing, you then want to then move on to injection molding. And one advice I will give is, why designing for 3D printing, you should be at the back of your mind thinking about injection molding, right? So you should add things like draft angle even in your 3D printed parts, so that you don't start from scratch or start things right from the start when you want to go into making tens of thousands of these parts. You should try to remove things like you should keep to constant wall thickness, even if you are dealing with 3D print, right? So I'll just jump right into the simulation and show you what happened then, when we ran the same parts, which was made for 3D printing for injection molding, right? And so say you have an engineer that is well versed in 3D printing and has very fair knowledge of how parts are designed for injection molding. You can just come into the tool, do a few setups, and he had his result right on his screen. And I'll just jump into the results. And don't worry, we are going to be looking at how to do this setup if we have enough time at the end. And so when I put each of the criteria, and which Fusion 360 allows you to do things like you put the materials. So let me just get out of the result. So first of all, you select the body, you put the type of material you want. There are a whole bunch of materials inside Fusion 360, and probably all the materials you need for injection molding. You set the injection location. You tell Fusion which of the faces is regarded as an aesthetic face, and usually the outer faces are aesthetic faces, and you can see it highlighted in green, right? And so you tell Fusion all of that. And, if we jump into the results, so let me jump into the results right now. So what Fusion, so after setting all of this, you then send it into the cloud, and Fusion gets back to you and tells you that, oh, look, that so you can see the first information Fusion is giving us. It's telling us that the time to fill will be about 1.72 seconds. It's also saying that with this setting that you've given me, your part may be difficult to fill with a time to fill of 1.72 seconds. So just 99% of the part is going to be filled up. So we are going to be having issues in some certain areas of this particular part. And I'm going to be showing you that in a bit. The future is also telling us that 4 faces on our model, we have sink marks, and 10 faces we have weld lines. 4 of these faces are going to be aesthetic faces, and this is actually bad. We don't want to see sink mark on aesthetic faces, and it's also letting us know that our maximum deflection is 0.87 mm, and the total time of this part to come out of the machine is about 17 seconds. We all know how important. So the lower time your part spent on the injection molding machine, the lesser amount you have to spend to pay the manufacturers, right? And then this is actually, so we're expecting this kind of error because we designed for 3D printing. And then just very early on in the process, we just wanted to check, okay, what are the defects in this part? And before we start to redesign for injection molding, although the best workflow would be to always think of injection molding while you are designing also for 3D printing. So I'm just going to be, going out of here and, jumping into what then happens when we want to design for, for injection molding. So just, give my laptop some minutes. Yep. So we have that. So let me just show you some of the features that that we incorporated into this part to ensure that it comes out well. So first of all, if you look at, let me slice this model. So if you look at it, there is there is a draft angle of about 1.5, which is quite recommended for ABS, right? You need to put at least a draft angle, even if it's a 0.5. Draft angles help your part to come out of the machine, right? So you need to put some sort of draft angle so that your part can easily get out of the machine, right? So if I go out of here, if I also check, the wall thickness is also quite uniform, right? If I try to measure it, although now due to the draft angle, it might not be accurate, but if I check this face and check this face, the wall thickness is about 3 mm. So it was because of the draft angle you are saying 0.998, right? So you want the wall thickness to be quite uniform, right? And for ABS plastic, you want to stick to 3 mm or just 3 point something mm as the maximum wall thickness, right? So ABS plastic is the material for this product. And then, so if you also look at this particular product, you can see each of the buses, they have ribs attached to them, which is recommended from the information that Felix gave initially. These ribs called gussets are all around the bus to ensure that it comes out well, right? If you look at the buses at the end, they are supported with ribs, just to keep to the rules of injection molding, so we don't have too many defects when we send this part to the manufacturer. But just at this end, if we look at this end, we can see that there is a possibility for undercut, right? So depending on where you put the pattern line, this particular slot or this particular cutout can be a big area where undercut might be an issue. And what will happen is that the manufacturer will tell you that you should use a side action, right? Something that you can put into the mold to prevent the material from filling up this space. So these are some of the things you have to, you have to start looking at when you're designing for injection molding. And if we jump into the simulation, again, I will show you before the end of this presentation how to go about setting up this simulation just very quickly, not so much into details, but that you can use to get started with. So and I'll then jump into the results. And let's probe and see what Fusion told us about this particular part that we designed for injection molding. So let's just give it a minute to come up, and yeah, this is it. So the first information that Fusion is giving us is that with these settings, our part will fill completely with a time to fill of 2.3 seconds, right? But from the former one, which was the one for 3D printing, the part at this right end was finding issues and filling up. But when we redesign, keep to constant wall thickness and follow all the rules, Fusion is letting us know that our part is going to feel well. It's then telling us that 5 of these faces are going to be aesthetic faces. The part material is still ABS, right? And if we say we should probe more, so let's look at other displays. Initially, I was on this particular display, the molding process, which shows us at a glance, right, what kind of defect we are going to be having. And if you look at the total time, it's 22 seconds here. It has increased from 17 seconds to a whooping 22 seconds. And that's a lot of money. Oh, sorry about that. Just give me a minute. So I mistakenly clicked the tab I'm not supposed to click. So So let's get back to the study that we are looking at before. Injection molding case study. Yeah, so we are writing. So then let's then look at other display settings. So if you can see where my mouse is under display, I'm going to be looking at the first one, so we can probe this more in depth. Right. So the first one is that our part is filling well, although the time has increased to 2 seconds, but it's filling up properly because we've kept to rules. We've started to use ribs at the different bosses, and we've ensured that the wall thickness is uniform. We've also added some draft angles, right? And so if we go to the next tab, which is the visual defects, and Fusion is still telling us that 5 of these faces are aesthetic faces. They were going to be having sick marks and all of that. So these are very useful information that if you send this to the manufacturer, like if you look at the first presentation that Julian gave, it takes about 8 to 12 weeks lead time for your part to come out from. So actually that's about that's about 2 months before you get your parts in your hands from the manufacturers. And imagine you have to go back and forth with all of these designs, all of these design changes. The manufacturer is coming back to tell you via email that look, you have to accept this recommendation, and you have to go back to your team, sit down in a meeting and do all of this. But with Fusion, your designer gets to see it right off the back of their screen, and then they design and see these suggestions right here. I know, we can then go deeper and look at these aesthetic faces, and we can zoom in the screen, right? And we can rotate our screen, and we can see that in different places we are having sync marks, which is bad, right? We are having different kinds of sync marks, and Fusion is then Fusion doesn't just show us the issues we are having. It's telling us that we need to reduce the thickness or the radius on the back side of features, right? So we used a 3 mm thickness initially, and it's telling us that we need to reduce these thicknesses. Probably we need to move the injection location to thicker sections of the modem, right? So Fusion is also telling us that move the injection location, modify the thickness. If we have more than one injection location, probably we need to reduce that. And if we jump into the warpage, we can see more results. And if we look at this more in depth, we can see that some section of our part is warping. So let me look at the front view. And if we zoom in, we can see that while this part tries to cool and solidify, it shrinks in, it warps. And so there's a warpage. And Fusion also gives us a warpage tolerance. So if you are new to injection molding, or if you don't have all the industry standard, Fusion can tell you that for this particular plastic, right, the warpage tolerance that is generally accepted is a 0.76, right? And your part is currently exceeding that warpage tolerance. Do you want to move on to manufacture this part or not? And that's up to you. You can do a lot of tweaks, which I'll be showing you in the next iteration. You can do a lot of things, to reduce this warpage that's happening to your parts, right? And so we can also compare between studies. If we click on this compare button, we can compare between different studies. We can start probe. If we click on this surface probe, we can click somewhere here, and we can see the warpage that this particular surface is undergoing, and it says 0.72 mm, right? So this particular surface is actually below, but at this end, we can see that the warpage is actually increasing, and this is where the warpage is actually highest, which is 0.80 mm. We can begin to probe and see places that we can reinforce with ribs and the rest of that. Right, so I will just go into the results. So there's another display called results. And what result does is that you can see a lot of settings: field animation, field confidence, quality prediction, injection pressure, flow front temperature. So the people that are very used to injection molding, they know how important all these settings are. And if you look at the field animation, if you just click play, Fusion can show us exactly how this part is going to fill up. If there's any issue, we'll see right here where the issue is coming from, and we can see that the part fills up, exactly how it's shown in the animation, right? So this can give you engineer a lot of insight. Where should I put the injection location, what can I change and the rest of that. So I'll just click on finish results so we can, we can jump into the final iteration and discuss more on that. So let's give Fusion a minute to set things up. Yes, so we are here now. All right, and so let's first of all, let's go into the actual design. Right, so let's go into the actual design and and do some discussions. So if you remember that at this side we had some materials going this way, and like I said, this material or that particular space can present a lot of problems for undercut, right? And the best solution, if you are looking at the part and looking at how everything is being assembled, is just to remove that piece of material and ensure that ensure that you can use a two-side mode, right? A very simple mode that that just comes in and then helps you. And this is actually quite cheaper than using a side action. You have to machine this mode, and the more time your part spends on the more time you spend machining this mode, it's a lot of money. And so the best solution to deal with this particular undercut was just to remove that particular material over there. First of all, it helps your part to fill up nicely and it saves you a whole lot of money. Secondly, because of warpage and issues of sync mark and the rest of them, we want to add ribs to certain locations of the part, right? We want to also make sure that in areas where they are where the thicknesses are not good, are not uniform. So we can see that this thickness is different from the overall thickness of the part. We want to ensure that we add very smooth transition, and also we've reduced the thickness from 3 mm to 2 mm, right? So we want to make sure that we take down the time the part spends on the machine. Remember that the former one was a 22 seconds. We are going to be seeing what the time is telling us here, right? So we want to make sure that the time the product spent on the machine is at a minimum. And if we can reduce the thickness to as low as possible that it does not affect functionality, that would actually be great. And in this case, we can take it down to 2 mm without affecting the functionality of the part, right? We want to also make sure that we add smooth transition to places where the thicknesses are not so uniform. And to all our ribs, we want to ensure that we have fillets to those areas. Again, we want to make sure that we have draft angles added to our parts, right? And if you look at this particular part also, it's not perfectly rectangular because rectangular enclosures are more prone to warping. It has some kind of curve just to ensure that we deal with the warpage issues and the rest of that. Again, our bosses have ribs, right? And keeping to the injection molding rules. So I'll just jump very quickly into the simulation and then let's see what Fusion gave us in that case. So first of all, our injection location is right in the center. Right, so let's look at the results. Let's very quickly look at the results. And if you can notice, I have 5 studies set up. So one good thing with this particular software or with our Fusion 360 solve different studies that you can set up more than one study and send all of that to the cloud, right, for you to get different results. So in this particular study, we have the material to be ABS plastic. In this particular study, we have the material to surprisingly also be ABS plastic. So let's look at another one. Okay, we have ABS plastic plus PC just to reinforce the plastic, right? We also have another study of another material right inside here. So you can pick different materials. In each of them, the injection location can be different, the processing can be different, and you can see how the results are coming along. I'm just going to jump into the results right now. Let's all probe these results together and see what Fusion is telling us. Yeah, so I hope you can all see my screen just to be sure that and you can hear me loud and clear.
Yes, Obiora, please go ahead.
Yes, yeah, so this is the result. So let's first of all look at the usual setting we look at first, right? On the display, the last one. So first, Fusion is telling us that it will take 1.36 seconds to fill compared to a 2.2 seconds that we saw in the initial study. And the overall time is an 11.63 seconds. Remember that this is still ABS plastic, right? The former one showed us about it showed us 22 seconds. So that's like half the time. So we're able to, by reducing the thickness, we're able to take it down by 50%, right? And Fusion rightly told us that we should reduce the thickness of our parts to deal with some issues. And it's showing us the result that this will take about 11 seconds, which saves us a lot of money and saves your company a lot of money also. We can also see it that it's saying one face on your model we have sync mark, 25 faces we have weld lines, right? One of these faces is an aesthetic faces. Previously we saw that about 4 to 5 faces and we have would be aesthetic face that would be having this sync mark and this weld line. But now we've been able to, by following the different recommendations that Fusion gave us, we're able to reduce these faces to about one of these faces having these defects. Like one of these faces are going to be aesthetic faces, and which is great, right? And so this is how far we can go with the software before we then send it to the manufacturer, and we can play with a lot of process settings, and the manufacturer can come back and give just 1 to 2 recommendations instead of a whole bunch of recommendations about your parts. Right, and we can also see that we've taken down the deflection to a 0.79, right, getting all very close to our tolerance of 0.6. Initially, it was a 0.89, right? And so if I jump into the guided results, just for us to see how things are. Now, if we move into the visuals and look at the aesthetic faces, we can see that you are not. So let's wait for Fusion to just set things up. Yep. So let the simulation view come up. Right. So we can see that if we look at the part, previously there were a lot of red faces, like a whole lot of red marks everywhere. We could see very large thick marks in every section of the parts. But by reducing the thickness, by adding the ribs to certain locations, and we've been able to remove a whole lot of sink mark. And the only sink mark, like how Fusion rightly pointed out, is just at this bottom region. And probably we have to add a very generous fillet to this side of the part to reduce that particular sink mark, right? And Fusion is also showing us that we are going to be having weld lines in some of these ribs, and with these settings now, or with this recommendation, we can then go to the manufacturer, and the manufacturer can tell us 1 to 2 things for us to do, and boom, we are already putting our part in record time. Right, so if we jump into the warpage, similar thing, we've been able to take down the warping to a 0.79 compared to when we're seeing warpage of 0.8, 0.89 at certain locations of the parts, right? And if we click on compare, like I said before, if we click on compare, we can compare between two settings. Remember, we have different studies. We have study 1. So if you look at study 1, right, we can compare study 1 with what's happening in study 5. And we can look at them on the same screen, but on different tabs. We can look at 4 different views. So we can compare 4 studies at a time. And we can, from our screen, start to make different design changes. And we can say, okay, let's go with ABS plastic instead of another material that we picked. Probably this injection location that is at this end is not giving us favorable results compared to the injection location at the center. So these are some insights you can get by using Fusion 360 injection molding simulation tool, right? And so I'll just show you how to look at the 4 grids. So we can change it from study 1 to study 6. We can change it to study 3. We can start to change the different settings to feel animation, feel confidence, and all those different settings that we use when we do injection molding. And the good thing is that we can do this very early on in the process. Like we can do this when we are designing. We can check all of this, and we don't need to go out of this software. We don't need to export our file to step file, taking it to that simulation environment. We can do all of this in a single software. We can collaborate with different team members. The design engineer can be working. The person that is an expert in plastic injection molding can also be working. Everything in one software, and everybody, using the same file at the same time. Right, so I'm just going to click on the finish compare, right? And then, now and then for the last part, I'm going to walk you through how you yourself and your team can leverage Fusion 360 to set this up very quickly. Right, so the first thing you want to do, of course, is then, do the CAD modeling, ensure that you have everything set up inside the design environment, and then you want to jump into simulation. So when you go into simulation, Fusion brings this tab up for you, right? Previously, the injection molding simulation was on preview, but right now it's currently among the studies, and we can then click on injection molding simulation. And just as a side note, Fusion does other types of simulation, static stress, other frequency, electronic cooling. So if you finish your electronic part right up here, you can take that product, and you can check if everything is fine with it. We have thermal, we have event simulation, shape optimization, and there's a study called generative design if you want to explore that. So I'm just going to click on create study. So let's all take a step back, and we can see the thing. So once you click on create study, the first thing you want to do, if you have multiple parts, you want to select the parts you want to actually run your injection molding on. So currently I just have one part on my screen, and I'm going to be selecting that part, and then I'll click OK, right? And so we wait for Fusion to bring up some dialog box. Right, so once I click OK, usually Fusion, you will see this particular dialog box come up. So it's actually because I've done the setup previously. So if you don't see it, very quickly you can go to setup summary, and Fusion brings up the dialog box, right? And so I'll just put this in the middle of the screen. The first thing we've done, we've selected our target body, right? The next thing we want to do is select the material that we want to use. So I'm going to click on study material, and Fusion brings up the material inside the software, right? And so inside here we have lots. So actually we have 12,116 materials currently. So that's a whole lot. And most of the popular materials that you use for injection molding are right inside here. And you don't have to start going through all of this material to select the best material. If you know the material you want to use, say ABS plastic, you can just search ABS plastic. You can, from under the drop down, select the ABS plastic, the type of manufacturers you want to go with. I'm just going to go into ABS plastic like this, and I'm going to pick a generic ABS plastic, right? So generic ABS plastic. You can as well, try to, if you know the actual ABS plastic you want to use, there are a whole bunch of them here, and I'm sure you would find the actual one you want to use, right? So I'm just going to click on select, and Fusion brings in that material into the simulation. And now the next step is, what is the injection location? Where do we want to put the injection location? So based on the mode you probably would have created in an inventor mode design, right? You can just click on injection location. You can select the location where you want to put it. And I'm just going to be leaving it in the center, right, for this particular case study. Which of these faces are going to be aesthetic faces? Which of these faces is your customer going to see? I'm going to make sure I select all the faces that the customer will be interfacing with, or that the customer is going to be seeing directly, right? Because sometimes you cannot hide some kind of errors like witness mark, like some weld lines, but you want to make sure that those weld lines and witness mark are not on the aesthetic side of the product, right? So I'm going to tell Fusion that, these are my aesthetic faces, and these are the places I want to come out very clean, right? And I'm going to say, okay. The next thing is asking us is So automatically, after selecting your material, your injection location, and your aesthetic phase, Fusion helps you to calculate the injection time automatically, right? Or you can just click on it and you can begin to play with the melt temperature if your manufacturer is starting the design process with you. They can tell you that, okay, this is the recommended melting temperature. But what Fusion does for you is that it shows you by industry standard what the recommended melting temperature is for ABS plastic, right? You can click on specified and you can begin to change each of these settings. If you have a plastic guy on your team, right? You can say, okay, I have played with my machine a lot and the shrinkage allowance is not a 0.6 mm. I can go up to a 0.8 and this part is going to be fine, right? So you can begin to change all of that. But by industry standard, this is it. And so if you don't have a lot of knowledge about injection molding, Fusion can help you take a lot of the work away from your hands and you can focus on the creative side of things of, making the product acceptable by the customer. So I can just click on OK. The melting temperature we've also set, right? And the mold surface temperature has also been set under here, mold surface temperature, melt temperature, and you can click on specify, if you want to change some of these settings, but these settings are actually good to go from here. And then, with just a few clicks, you can then click solve. And within a matter of time, so this study takes about 15 to 30 minutes to come out. And, for you to send this study to the cloud, you have to pay something called cloud credit. I'm not going to be getting into all of that, right? Unfortunately, you cannot solve injection molding locally, although you can do static stress locally. But because of how intensive this study is going to take, we have to send it to the cloud to get the results, right? So, this is just a quick way for you to set up your study. If for any reason the setup summary doesn't come up, you can always go from left to right. So, if you want to simplify your model, you can pick the target body here. You can select the material. Yes.
Yeah.
So I'm just going to leave it at that, and I'm going to, open up for questions and all the rest.
Okay. Oh, thank you so much, Obiora. To be honest, this looks like something we don't want to stop looking at. So maybe what we can do is likely have maybe a follow-up session. But for now, let's just quickly take some questions before the 6 minutes time gets off. So firstly, I know Latif Balogo wanted to ask some questions. So please, if you can just unmute yourself and briefly ask your question. So let's take it on from here. Latif? Okay, I don't know if Latif is with us.
Okay.
Okay,
Oh,
Latif.
thank you very much. Good morning, everyone. My name is Latif. Obiora, thanks so much for the wonderful presentation. You've actually answered some of my questions towards the end because I wanted to ask how the costing process for this new adding into the software is like. I wanted to know if it's similar to the generative design where you have to pay for cloud credits, or you can solve the simulation manually, like static simulation in Fusion 360. All right. The first question I want to ask is it possible to have a customized plastic material? For instance, you're looking for a specific material field, probably polypropylene plastic material, and you don't have that material in the 12,000 list of material we showed earlier. Is it possible to customize the material? That's the first question. Then second question is it possible to have a symmetricity in your analysis? What I mean by symmetricity is this: when you're doing a static structural analysis and you have a very complex part that will take a whole lot of time to run, and you probably want to section the part into probably 2 or 4 different, you want to use your symmetric plane to divide the part into 4 or 2 different sections. Is it possible to have a similar analysis in plastic so that you refine your mesh properly and then you get a better result. Then the third question is it also possible to have a multiple, probably to set up a parameter with multiple value and see the different outcome to compare? Probably you have a constant wall thickness, or you have a constant draft angle, but you have a varying thickness. You want to see how your thickness will affect your runtime. Is it possible to just set up your thickness value and see the value of your runtime at the end of the day and compare which is the best solution for you to choose from? So those are the few questions I have for you. Thank you very much.
Okay. Thank you, Latif. I'll take the last one. Yes, you can do that with studies. So there are various studies you can set up. You can set up as much as possible, and then iterate or play around with some parameters. So, but I'll let Obiora just take the two: material customization and symmetricity in simulation. So, Obiora, please.
Thank you, Julian, and thank you, Latif, for your question. Well, currently, as an injection molding simulation came out last year into Fusion 360, right? Currently, you cannot do the symmetricity as you usually do with your static study and other type of study for you to reduce time of for you to reduce your time in the cloud, right? So that functionality is not here yet, and I'll probably have to be looking at the roadmap to see if that functionality is going to be coming into the injection molding and simulation. But one great thing is that despite all of the different things I showed today, more is yet to come into Fusion 360 injection molding simulation workspace. So you just have to, you just have to keep an eye out for that, and hopefully the future you're looking for is going to be coming very soon, right? In terms of material and customization, right? And so currently, right, and to my knowledge, the material you can select is the material inside Fusion 360, right? And so currently, and I'm also currently looking at it, you cannot do much of an edit into it, but you can look at the different descriptions, and there are a whole lot of material. And the first thing you want to do is check if the material you are looking for is right inside here, right? And before you start to look at them, and probably that material is going to be right inside Fusion 360. But currently, there's no way for you to add customized material, but I'm sure that will be coming out,
Thank you,
very soon.
Thank you, Obiora. So, Latif, what you can also do is, with the development of Fusion, the way it's designed, right? You can actually make contribution, all right, and probably contribute or recommend that that similar feature as you would have it in Inventor comes into Fusion 360, and I believe in a very short period of time we'll have it in Fusion 360.
Well, this is not a question, this is more or less like a suggestion anyway. During the early phases of the generative design analysis, I think they gave free cloud credits for early users for us to quickly adopt the generative design study, for us to familiarize ourselves with those and play around with the new add-in, so that by the time we start getting charged for the cloud credit, we understand when to use the cloud credit and what exactly we want to do. Do we have something similar in this injection molding add-in?
Well, so Latif, you can actually do have a trial, right? But this particular question you're asking of where they give you free cloud credit for you to try it out was actually done last year. So before this study was released, there was a preview and everybody was able to use it for free. So for your particular question, that was last year. But there are other ways for you to test it out.
Okay, thank you so much, everyone. I'm not sure. Is there any other question we have at the moment?
Yeah, so there's a question about the recording, right?
Yes. The recording will be shared automatically. So just a few minutes or a few hours after the session, you have it.
There's also a question from Afolabi Muhyiddin about card training or something like that. So you can always reach out to Generative Card on LinkedIn, and then we'll take it off from there.
Yes. So also I know that the generative CAD team will reach out to you even before you reach out to them. So no problem. Yes, you have generative CAD have it covered. So I'm not sure if we have any other question unanswered right now. So okay, so what we do as a follow-up to this session is we'll try and reach out to everyone, for your specific questions, specific clarifications. And then also we'll likely set up a follow-up session to these, all right, that will be all 100%, it will be 100% demo, all right, so we can see how this thing works, all right? So, but please do not hesitate to reach out to us to see how we can help you and your organization adopt these technologies and this solution. All right, we are all available. Our details will be with you shortly, or we'll reach out to you. And we are all available in country. And myself, Julian, I also cover a wide range of West African region, Anglophone speaking country. So we have a whole lot of reps here. We have Worldview from South Africa and Generative CAD from Nigeria here. So I think at this point,
Julian?
yes.
Okay, so just to round up, I think just thank you so much, Latif, for your questions and also kind of insights, and for Julian Obiora, thank you, and all for our amazing audience, kind of holding from beginning to end. So we'll all kind of call here for, yes, this slide, this recording will be shared for all who is here. So as far as the email you used to register will definitely be shared with you. So we just reach out to us, while we share this, content and follow-up emails, like if you want to have, like for your team, how can you start implementing Fusion with your team, or probably, instead of leveraging on thinking about maybe, I want to buy Fusion, okay, to integrate it, like Fusion is like the kind of like most affordable software out there that can do so much, we probably want to have that conversation with you, or for training, or for consultant, or any other thing. Just reach out to us. We're really open to have that conversation to help. The major aspect of it is to take it from point 1 to probably point 2, point 3, or point 10, if that's the case may be. So thank you so much for being here today, and we hope to have more further sections. We didn't plan for it, but I think probably it's kind of something we'll probably have to plan in nearest future. And we'll also definitely let you know that when we are planning for that and when that will happen. And so any further questions, any further, reach out to us, and I would very, very, very happy to work with you and your team and make sure that we'll take you from and achieve from point 1 to point 10 and achieve that highest level of productivity your team envisions to have. Thank you so much. Over to you, Julian. Hello, Julian. You can round up.
Oh, sorry. Thank you so much for joining us today. It was a pleasure having all of you. All right. And at this point, we'll be closing the call, and I wish you all have a nice day today. Thank you. Bye-bye.
Bye-bye, everyone.
Yeah, bye-bye. Thank you so much. Bye-bye.